Welcome everyone to Devnexus here in my hometown of Atlanta. So this is one of my favorite conferences because I don't have to take my shoes off to get to this conference, so it's very nice. What I want to talk about today is this common question that may come up in your organization, which is, why can't we just decide this architecture issue once and for all and stop talking about it? Why can't we just say everything in microservices is going to be choreography? Done. We don't have to address that decision anymore, but it turns out the kind of defining characteristic of software architecture decisions is they defy your ability to do that, and I want to talk a little bit about why that is today. And it really touches on two parts of this ecosystem: how you structure software architecture, and then the way to sort of get yourself out of this problem is around mechanics. So let's talk for a second about architecture versus design. You may have noticed on the opening slide, I've just published with my co-authors Mark Richards and Raju Gandhi a Head-First software architecture. The Head-First series, of course, is almost like a graphic novel version of a technical book. And in it, we finally addressed a question that we very purposely avoided in our Fundamentals of Software Architecture book. But we've been asked about it so much since then, we felt compelled to write about it, and Head-First is more of an introductory book, which is, what is the actual difference between architecture versus design? Because if you're going to make architecture decisions, you need to understand this first, because some of these decisions are more important than others. And like so many things in software architecture, there's not a nice, clean, binary definition here, but it's really about a messy spectrum of how much is this decision architectural versus how much is this decision about design. And those things are contingent upon several factors, one of which is architecture decisions tend to be more strategic. This is a direction that we're going versus a quick fix for something, which would be tactical. Architecture decisions tend to require high amount of effort, both to implement it and then to change it later. So choosing a particular architecture style is an architecture decision because it's very difficult and a lot of effort to change that later, versus design things, much less effort to change later. And the real difference though, and this is in fact one of our favorite definitions of software architecture, is a software architecture decision is one where each choice has significant trade-offs. In other words, there is no clear-cut best practice. You always have to evaluate trade-offs. And think for a second about this concept of a best practice, which is widely kind of made fun of now for good reason, and especially in software architecture, because the idea of best practice is whenever this situation comes up, I can just turn my brain off and automatically do this thing, because this is a best practice. It's not even a better practice, which would allow you a little bit of argument. It's a best practice. So there's no argument, we have to do that, it's the best. But you can't have that in software architecture because there are always significant trade-offs to be assessed. And that's really the secret of why these software architecture decisions are so intractable. And so when you look at choices like, we're considering using microservices for this new system, clearly an architecture decision, strategic as a direction, super high effort to build it and change it later, and significant trade-offs included with it. But what about things like, we need to move the cancel button to the bottom of the screen? Trivial, easy to do. We could do this in a matter of minutes or hours, and so very much a design decision. We're considering breaking the single payment service into separate services, one for each payment type. This one's a little trickier, because initially it sounds, that's not so bad. Sounds pretty simple, but this is what you have to do as a software architect always, is evaluate trade-offs. And one of the techniques that we talk about is model relevant business use case scenarios to see what the trade-offs are that come out of it. Here's an example. Scenario one, we're going to update credit card processing. What would it look like in the single payment system versus the individual ones? And this is going to get to a problem I'm going to address in just a second. What is the correct granularity for services and microservices? The philosophy is it should be single purpose. Okay, that makes it clear and easy to understand now. But is payment single purpose or is each kind of payment single purpose? Now we can have a good debate over lunch about what is the definition of single and single purpose. You need better tools for that, and this is one of them. So, but we'll talk more about granularity in just a second. So scenario one, upgrade credit card processing. What is it going to take for both of these? So for one on the left, I need to update the code for credit card processing. I may impact the change in the database. And I probably need to test all of it just to make sure I haven't accidentally broken something because it is one code base. Versus over here on the right, microservices, decoupling for the win. Fantastic. Isolated scope of change, very small scope of that change isolated to a single service. So when I have separate services, I have better maintainability, testability, and deployability, which is nice to have. Scenario two, add a new payment type. Let's say we want to take reward points. Okay, in the single service case, we add reward points, but that means we're going to have to make some changes and probably have to change and test, etc. But over here, decoupling for the win, just add a new reward point and we're done. And so separate services give us better and easier extensibility. This is looking kind of like a blowout, so let's just do one more to see. What about if we want to use multiple types for payment? I want to put part of it on my reward card and part of my credit card. Easy over here in the single service. I can do transactions. It's all one bounded context, and so this is easy to make sure everything works correctly. Over here on the right, now I have an orchestrated workflow that has to resolve transactionally, which means now I have to have not only an orchestrator between these things, but now I have to worry about distributed transactions, which is a major headache and very difficult to get right. In fact, pretty much the second half of our book, Software Architecture, the Hard Parts, tries to address this really nasty problem right here. And so separate services give you a big performance hit because now I have to do all this coordination, and data consistency problems because of transactionality is very difficult to achieve here. And this is the kind of trade-off analysis you do all the time. And in fact, I'll show you the outcome of this particular trade-off analysis, because once you've done the trade-off analysis, you have to figure out, well, how does this apply to my organization? So as you can see, this one is not so clear-cut. There's definitely some architectural aspects to this one. But this gets to our first law of software architecture in our fundamentals book. Everything in software architecture is a trade-off. And there's a corollary to that law that if you think you found something that isn't a trade-off, it probably just means you haven't identified what that trade-off is yet. And the classic example I bump into all the time when I talk to organizations as a consultant is I hear some variation of this sentence a lot. We really like this idea of highly decoupled microservices because it allows us to make small scope changes and move really quickly. But as an organization, we want to achieve a high degree of institutional reuse because we don't have to rewrite a lot of stuff over and over again. So that's our dual goal. And I have to explain to them, well, that's not possible because high degree of reuse, how does reuse work architecturally? By coupling. You cannot have a high degree of reuse and decouple at the same time because the very act of reuse is coupling. And so identifying what those trade-offs are is important because then you can make a value judgment. Which of these is more important to our organization? Here's another classic example of the kind of trade-offs you do all the time in software architecture. And this is not even microservices. These are event processors with a single database. And here's the question you have to answer as a software architect. Should the event payload include all the data necessary for processing or only the keys? In other words, should I, at the beginning of this workflow, use this orchestrator to query the database and populate the entire thing into one record, pass that information to payment, pass it to inventory, and then reconcile that back to the database one time? Or should I just use the keys and let them query it as they need to? So here are the two scenarios. I query from the orchestrator, get all the relevant information out of the database, populate that into this message, and then send that message to payment and to inventory, and then write that back into the database once that is finished. The alternative is just go to the database and grab the key, pass the key over to payment and inventory. They query the database to get the relevant information they need to do their workflow, and then they write the relevant things back into the database when that workflow is finished. So, which is better? Well, it depends, which is the answer to every question in software architecture. The unfortunate problem for you, though, as a software architect, is now you have to answer the follow-up question, okay, depends on what? And here's what it depends on. So if we populate the entire thing one time and pass that around, I get much better scalability and performance. Because what's my scalability bottleneck going to be in this topology? It's going to be the database. The fewer times I hit the database, the more I will be able to scale this thing to a large number of users. But now I have contract management and versioning issues. If I'm going to start passing this thing around, this is not a snapshot in time. These things are going to change. Now I'm going to have to start versioning them, which can lead to its own set of headaches, etc. But the other subtle problem here is one called stamp coupling. And I want to focus on this a little bit because this is one of the most common mistakes I see architects make exactly around this desire to say, I just want to decide this one time and be done with it. And it's around the way you pass information between services, what protocols you use, things like gRPC, which is very popular, or REST, etc. So let's talk a little bit about stamp coupling. This is an ancient picture. This book that this comes from on Wikipedia comes to us from the 1980s. This is so outdated, in fact, that the tight coupling up here, your programming language won't even let you do anymore. That's why we have private in languages like Java. But the next to last one there, stamp coupling, still exists and is actually quite common. The origin of this comes from the COBOL days, which is how old this is. Data structures change so infrequently in COBOL that they literally got rubber stamps made to represent data structures so that when new problems came along, they could stamp it to say, use this data structure. Can you imagine your database is changing so infrequently that you basically put the schema onto a rubber stamp? You can stamp on, so that was the days of COBOL. But here's what it looks like in the modern world, and this is a very common problem. So let's say I have this profile service that has all this profile information about customers, clients, etc. And I have a wish list service that has all the information it needs about a wish list except their name, because the profile is the owner of the name. Wish list has everything, including the ID, except the name. And if I want a workflow to be able to return Mark's wish list, for example, I need to make a call from wish list over to profile service. But you'll notice in this solution, I'm using JSON, but I'm using JSON schema, which is a way to bind metadata into JSON communication. This would be similar in something like gRPC as well. And so I just bind the profile to wish list, and I reach over and grab the info from profile, wish list, and grab the name out of it. This is what we refer to as an overspecified contract, and this is stamp coupling. And here's the problem with this. I'm introducing brittleness into my architecture where it shouldn't be. And here's why. At some point, somebody comes along and says, hey, I notice you have state in this. Is that this full state name, or is it the two-letter state code? You go, oh, yeah, you're right, that's ambiguous. We should really change that to state code to make it a lot clearer of what we're actually doing here, which of course changes the profile service and now breaks the interaction between wish list and profile. Even though wish list doesn't care anything about states or state codes or any of that stuff, because I've overspecified the contract, I've made it brittle, because now I changed something nobody cares about and yet stuff breaks. This is stamp coupling. Still exists quite commonly in places where things are joining, like platforms where you overspecify contracts and make them too tight. You make your architecture a lot more fragile and brittle when you do that. So looser contracts create less brittle software architecture, which is of course one of our goals when we do this kind of work in software architecture. So stamp coupling is possible because I'm hydrating that entire contract, and of course there may be places where I don't need something in payment that inventory needs. And then finally I have multiple systems of record. If I've hydrated that entire contract and passed it around and I reconcile it, what if it's changed in the database in the meantime, so I have to worry about that? So what happens if I just do the keys? And each of those services then have to go and hit the database themselves. Well, scalability and performance are not going to be as good in this case. However, I have a single system of record. I don't have to worry about data consistency stuff. The data itself only lives in the database. I'm only passing keys around. I don't have to worry about stamp coupling, bandwidth, or contract management issues because, again, it's all just inherently there in the database. And so now I have a reasonable matrix to do a trade-off comparison here. Now I can go back to the organization that needs this workflow and say, okay, how scalable does this thing really need to be? Because if it needs to be super scalable, then we can figure out ways to manage all of these headaches, but if it doesn't, then we have a clear choice here because it eliminates the most of the headaches and doesn't, if we don't need extreme scalability. You do this kind of trade-off analysis a lot in software architecture. But this actually points to something that Mark and I talk about sort of as subtext in both of our books, which is really the essence of this idea of agile software development and architecture. Agile software development doesn't mean no architecture. What it means is fast feedback on your architecture and your design. And one of the things that Mark and I love to talk about is incremental design in software architecture. And this is an example of that. Let's build two candidates on paper and then do a qualitative trade-off analysis to see which one looks better before we actually implement code. But let me show you a much more common activity around this, which is around service granularity in microservices. This is one of the things that people struggle with the most, particularly when they're new to microservices. What is the right level of granularity? And you can have tons and tons of philosophical discussions about this, but I want to get to an engineering approach to solve this problem. The way to think about this is that as an architect, you have a toolbox. Now, if you've ever seen a specialist workman, like a woodworker, they have common tools like screwdrivers and hammers and wrenches, but they also have some really funky specialized tools. You know, a curlicue thing with a scoop on the top is like, what is that thing for? But you know, there's some use very specific for that. You need to think of this as the same way as a software architect. You have a toolkit and you need tools to do architectural design. And some of them are going to be fairly generic, but some of them are going to be hyper-specific to your organization and your kinds of problems. So I'm going to give you a starter toolbox today for determining granularity. And there are two categories of tools that we talk about here. Disintegrators, which are forces that encourage you to break things down into smaller pieces, and integrators, which encourage you to bundle them back together into bigger pieces. I will talk about 5 disintegrators and 3 integrators this morning as a good starter kit. These are fairly generic ones. This is like a Phillips head screwdriver and a flathead screwdriver and an Allen wrench. So let's talk about these and how they apply. The first disintegrator is maybe the most obvious one, service functionality. I want to break this down by behavior. And this is what happens when you give developers a monolithic application and say, break this down into microservices. They will break it down into the teeniest, tiniest little atomic pieces you can imagine. So if I have a notification service with text, email, and postal letter, and I apply this disintegrator to it, then what I'm going to end up with is individual services, each for the individual behaviors of my domain. This one is easy and fun to do, particularly as you understand the domain. However, notice that if I have something like a customer service and I break it using this disintegrator down into profile, comments, and preferences, I'm not trying to turn this thing inside out. In other words, I'm not creating a profile service for all profiles for all entities in the system. This is still a customer profile. The point of this is that this disintegrator doesn't overcome common sense. This is still about customer, and I'm breaking customer down into smaller pieces. I'm not reorganizing it in some kind of technical partitioning. So we talk about this sort of like the strong nuclear force and the weak nuclear force in physics. The weak nuclear force never overcomes the strong nuclear force, which would be the domain boundary here. But that's only one of our disintegrators. The second one doesn't have to do with the behavior of the code at all, but rather how volatile that code is. So when you look at something like a notification service and the code rarely changes for text and email, but because of weird regulatory rules about wording and the postal service, we have to constantly tweak the code and behavior of the postal letter. And so the smart way to break this apart might be electronic notification versus letter notification, because one of these, the code rarely ever changes, and the other one, it changes a lot. Now, there are two little asides that I want to make about this one. The first one is there are these weird little cults that grow up in software architecture over time. About 10 years ago, there was a group of people that were called variously either Rastafarians or followers of Fielding, who believed that every problem on earth could be solved with rest if you just find the right way to use the 4 verbs, which are spoken about with reverence, the 4 verbs. It was a dissertation. It's not meant to be a life philosophy, but a lot of people really bought into every problem can be solved with rest. Another one of those little cults is volatility-based decomposition. You hear people say, oh, that's the only thing you should ever look at is volatility, because in the world they live in, there's a clear distinction between volatility of some versus the other. But this is just a tool in your toolbox that's useful sometimes and not, but it's a good guideline because of the second little aside here. I was talking about reuse earlier and coupling. That's one of the classic things people get wrong about reuse. There are 2 things that are important about reuse. And everybody gets the first one right, and everybody messes up the second one. The first one about reuse is abstraction. Oh, look, I could abstract this out of here and use it from a bunch of places, making it a good candidate for reuse. The thing everybody gets wrong is the only way that's a good kind of reuse is if it has low volatility. Because if I couple to something and it's constantly changing, everything that couples to that thing has to stop and react to that change, which causes ripple effects all through your architecture. This is why, by the way, the things that we most effectively reuse are things like plumbing, frameworks and libraries, and this is also why domain concepts are terrible candidates for reuse. Because what changes the fastest in the piece of software you're writing, the thing you're writing the software about, which is the domain. So resist the temptation to create a single customer service that owns everything we know about customer, because all you're doing is creating a rippling nightmare within your ecosystem. And so volatility is the second important aspect of is it really reusable or not. The third of these is scalability and throughput, which is kind of a shorthand for this whole family of operational architecture characteristics like elasticity, scalability, et cetera. So for example, if I have SMS, email, and postal letter, and SMS gets a huge amount of traffic and postal letter gets almost nothing, then I might split those apart in 3 separate services, SMS, email, and letter. But looking at the magnitude, I could probably take email and letter and put them into the same service, but what would I call it? Naming things is hard in software. I could call it non-SMS messages, but that seems really wrong, naming something because of what it's not. And this is another case where, reason and logic will overcome your desire to bundle them together, even though they have similar characteristics. They should stay apart because it's not going to make any sense if we try to break the strong nuclear force of the domain. The fourth of these is fault tolerance, availability, reliability, et cetera, and that family of architecture characteristics. So if part of my system is very fragile and crashes a lot, then that's going to bring the entire thing down if that's running as a single process somewhere in a virtual machine or container or something like that. Separating those will isolate that volatility, so if one of them goes down, I have more insurance, and I have circuit breakers and other techniques in DevOps to help manage that for individual services. And then finally, access restrictions, security restrictions, information, et cetera. So if I have something that has sensitive information like financial information or PII, health information or something like that, I may want to break those down and get better control over that. So here are 5 disintegrators that you can use in distributed architectures. And these developers and architects kind of stumble upon, but the integrators are tougher. And I'll talk about 3 of these. And the first of these is transactionality in database transactions. So if I've used another disintegrator and broken down my profile service into 2 pieces, one that contains a profile and the other contains passwords, but then I realize when I register a new customer, I need to make sure the password is saved before I can save that customer, which means transactionality, which is frowned upon. It's not impossible, but it's the last resort. And so one of the ways you could think about this is, well, one way I could solve this problem is just don't build separate services and bundle it back into a single service again. Now the transactional boundary is back at the service boundary. And this is a great example of this idea of iterative design. You create a candidate architecture, and then you look at some of the issues. Oh, that's going to cause transactionality. Let's bundle it back together. Is there a different disintegrator I can use on it that still gets the out of this particular problem? The second of these is data dependencies. This is, of course, one of the distinguishing characteristics of microservices, the data fidelity in microservices. And this is a really common scenario where I have a single service and I want to break it into 3 other services, but of course it has data dependencies in it. And so I can't just have all 3 of those talk to the same database. That kind of defeats the purpose, particularly in microservices. So now this becomes the kind of matching game you did as a kid. So it turns out that function A writes to 1, 2, 4, and 6, and reads from 5. B writes to 3 and reads from 2 and 5. And then C writes to 5 and reads from 2 and 3. So we'll just do the sliding puzzle game here, and we'll say that whoever writes to it owns it. And so service A owns those, service B owns that one, and service C owns that one. Okay, good, we're finished. We can move out and go out. Oh, wait a minute, there are a bunch of arrows left over, aren't there? That's probably not good. So how do you manage that? Well, you could say, well, just let this one read the database over in that other service, and let this one read that database over there, and well, you can see where this is going. That's no good. This is actually worse than what we started with. There are ways to resolve this with caching and a bunch of other complicated architecture patterns, but one way to solve it is just don't break it into multiple services. Just keep it into a single service, and now the data dependencies don't have to reflect a new level of granularity. This is very often the governor on a team's desire to go crazy with the service functionality disintegrator. And then the third of these is workflow and choreography. So I have a single service over here. It's too big, too much responsibility. Let's break it down into multiple pieces. Okay, great, but now the problem is I still have to do that workflow. And it takes a lot longer to call across a network than it does make method calls and database calls within a single context. And so responsiveness and performance will likely suffer here. So if it took 1,500 milliseconds over here, but now when I make this call, I've got to do all these hops and from one service to the next one and aggregate and consolidate and return. Very often this is a lot slower. This is an unpleasant surprise for a lot of people in ecosystems like microservices. But then you have to worry about reliability and data consistency too. What if one of these things is down as I'm trying to do this workflow? What is the state of my data? Again, there are patterns you can use to do this, but it's a lot of work to make that happen. And so workflow and choreography, sometimes, let's not break it apart because it's causing more trouble than it's worth. And one little aside here, recently, we're very reactionary as a community. Very recently, Amazon announced that they were moving part of their workflow away from step functions into a single service, and the internet just went completely ballistic. Amazon is abandoning microservices and going back to the monolith. It's like, no, they're not. They're just applying an integrator because they've realized that they've got a bad set of trade-offs, and they're changing their trade-offs just by changing their architecture structure. Calm down, no one's throwing away microservices in favor of the giant monolith. So I want to stress that this is really just a beginner kit. that it's up to you as an architect to start with this, but then look for these things by name in your organization and tell other architects the names of these things, because these are really effective domain-specific patterns inside your organization. So I call this keynote, What Makes Software So inTRaCtAbLE, but maybe I should have called it something like, how do you make it more tractable? Because that's really what you want to do. And this is where the other side of incremental design and architecture comes in, and it's the mechanics of this idea of architectural fitness functions. This is something we created in the evolutionary architecture book, this idea of guided change in architecture. These are basically the architectural equivalent of things like unit tests. But unit tests are designed to look at your problem domain. These are designed to look at the capabilities of your system. And they are necessarily a little more complicated than your unit tests, because your unit tests are in a particular unit testing library, but fitness functions encompass a lot of things like software level metrics. More about that in just a second, which has become increasingly important, much more so than you may realize. Things like unit testing libraries that specialize in this. But some architecture characteristics like performance and scalability need monitors, and so you use monitors to implement fitness functions. Chaos engineering, which was founded by Netflix, is a perfect example of this idea of stressing your architecture and assessing it in real time. And we've seen a rise in a whole lot of these tools recently that allow you to do some really, really clever things. One of these is ArcUnit, which is inspired by JUnit, uses some of the helpers from the JUnit world, but this helps you build architectural fitness functions. Maybe, for example, you're annoyed as an architect for developers who throw generic exceptions. You wire this predefined governance rule into your build, and now no lazy developer can throw a generic exception again. They must properly subclass exception so that you know what you're catching. You're not having to parse a message to figure it out, etc. So this will let you restrict what can be used, encourage use, etc. But the real use of tools like this, let's say that you design a layered architecture with a presentation layer and business layer and a data access layer, or some other partitioning like microservices, and you want to control communication. But you design this as an architect, but you hand this over to a group of developers to implement it. How can you make sure they're going to implement it correctly? Either because they don't understand the value of this separation, or maybe they're more likely to ask forgiveness than permission. And now maybe nobody will notice, and by the time they notice it, it'll be too late for them to do anything about it. How do you preserve design decisions in architecture? Here's how you do it. This is from ArcUnit. It uses the Hamcrest matchers. No classes that reside in a package service should access classes that reside in a package controller. This lets you check the internal structure of your software as it's being built, which is really, really nice. This is the equivalent tool in the .NET world called NetArcTest. There's an equivalent tool in the Python world now called PyArcTest. There's one in the JavaScript world now called TSArc. So these architecture validation tools are starting to show up in all sorts of different ecosystems. But don't just look for a tool, because here's what you really want as a fitness function. I have this orchestrated workflow, and I have these domain services. I want to make sure that none of these domain services talk to each other, because the orchestrator has the state of the workflow, and I don't want them talking behind its back and things getting out of sync. So where's the framework or library that I can download to write that kind of fitness function? Unfortunately, it doesn't exist, because there are way too many variables here, because it's software architecture. What are these things written in? They may all be written in different things, because we're in microservices land. What kind of database are these things using, if at all? What kind of communication protocol? Synchronous, asynchronous, gRPC, REST, message queues, events. There are way too many variables here to think that you can find a framework or library that already knows what you're interested in. But this is a failing for a lot of architects, because if I can't find a turnkey tool to do it, then it's just not worth the effort. But the first question you have to ask yourself for ecosystems like this is the information I'm interested in available somewhere? The answer is yes. All these services know exactly who they talk to and can log that information. And so now, as an architect, what I need to do is write 10 lines of scripting code to say, gather up the information that's already there and then validate to make sure that it's doing what I want it to do. Import each of the services, grab their logs, and unless they're only calling to the orchestrator, then raise an exception that something is going wrong here. So most of your architecture fitness functions are in fact not written in the language of your solution, but in scripting languages like Ruby or Python or Z Shell or something like that, because you're just aggregating some little interesting bits of information together to make them useful. Fitness functions are useful at all different levels of your software architecture stack. From the coding level, up through things like integration architecture, and even up to things like enterprise architecture. You can use these to validate the engineering aspects of what you're actually building, and particularly true at, for example, the platform level. So fitness functions for capabilities like performance and scale and elasticity, et cetera, and then well-defined contracts at boundaries to prevent brittleness between bad things happening within your software architecture. So let's wrap things up with a few little traps around trade-off analysis and actually go back and answer the question I posed earlier today. Not this question, this is another question that we're answering here. What happens when there are no best practices? In fact, the architectural fitness function thing is really important because increasingly you're not going to be writing code. You're going to be governing code that's been written by a machine. We're going to do a lot less actual writing code and a lot more validating that the code that has been generated actually makes sense. Now, if it's just a throwaway project, then who cares how ugly it is? But if you're trying to build a foundation, a platform for something in the future, we're going to have to make sure that things like internal structure, coupling, cycles between components, and those kind of things are not being inadvertently created. More about that in just a second. But ultimately, this is why the job of software architect, I think, is safest in the technology world from AI, because we can't even teach humans how to be good software architects yet, much less teach machines how to do this. And here's why. Because within an organization, the driver for all that trade-off analysis is the problem domain. Your business gets together and says time to market is a really important thing. So as an architect, you analyze architecture characteristics and look for things that get you faster time to market, maintainability, testability, deployability. Then when you do trade-off analysis, you look at what are the trade-offs here, and if you get something like performance versus maintainability, you go back, oh, maintainability is the most important thing. That's going to be the trade-off that wins this time. Because a lot of these trade-offs are not objectively better or worse, they're contextually better or worse, and you have to understand that context, which originates from the motivation for writing this piece of software. So this is the thing that's going to drive you to choose one thing versus another. So here's a trap to watch out for, the out-of-context trap. So let's say that you have an architect that says, I can't decide whether they do shared libraries or shared services for common functionality. A shared library means I have a jar file, for example, that gets compile time built into services. A shared service is I just make a call at runtime to get that information. So which of these is better? Well, you go, of course, to the matrix to try to figure that out. So heterogeneous code is a lot worse for the shared library because now every time I need one library for each tech stack, much better for the shared service. High code volatility is it's worse for the shared library because every time it changes I have to recompile, whereas you just get the new version when you call it. Versioning is easier in the shared library. I don't have to worry about any kind of runtime behavior. Change risk is easier. Once it's compile time bound, I'm pretty confident in it. Performance is better. Fault tolerance is better. And scalability is likely better. So if you just look at the trade-off analysis, okay, we have a clear winner here. But then the context comes in. Oh, we have services in 4 different languages, and fault tolerance isn't a big deal for us. That means that these 2 are weighted more heavily than the others, and this is ultimately what we're going to decide, because when you do these trade-off analyses, not all of these things are weighted for exactly the same values. Remember this problem that we started things out with. I wonder if we should have a single service or separate, single service, single payment or separate services for each one. Now we know enough to answer this question. Now we go back to the original motivation for this thing and look at which one of these has better maintainability. We're going to choose this one even though it has a more difficult problem multiple types, because what's most important in our ecosystem here, maintainability, and this one gives you better maintainability for that. So this idea of architectural fitness functions is really about governance. And for a long time, governance was about architects looking after professional coders to make sure they're not making little mistakes and things like that. And so a lot of those fitness functions that we talk about in our book govern internal code quality. And they're sort of an interesting aside in a lot of organizations, but we're about to see a tsunami of functioning but terrible code show up at your doorstep. It's going to work, but it's going to be objectively awful. This is going to be the job of developers and architects going forward, is governing what's built by machines, not governing what's built by people. These internal code quality things that we're kind of blasé about now, things like cyclomatic complexity, things like abstractness, instability, normalized distance from the main sequence, these are all objective engineering ways we can assess the quality of code that has been generated by machines to make sure that we're building a good foundation. This is where a lot of our effort is going to be soon, is shepherding the mountain of code that is going to show up at your doorstep and make sure that it's actually worth using that code within your ecosystem and making sure that it does what it's supposed to do and it's safe. And I'm out of time, so thank you very much for coming, and I hope you enjoyed it. Thank you. Thanks.